All right. Well, by my clock, it's 7, so we're going to go ahead and get started. My name's Aaron Larson. I'm the technical services manager for Gensco. I've been a train FSR for about 14 years now. I guess going on 15 here. And today we're going to walk through defrost controls. We're going to talk about sequence of operation, troubleshooting, and what to expect in defrost controls. This is kind of a neat little picture of the seat lab in Tyler, Texas. I believe it's every Wednesday and Thursday. It snows in Texas inside the lab here, and they do some very rigorous testing for our systems to make sure that they're going to perform as we expect out in the field. And luckily for us, the Pacific Northwest has some of the worst defrost areas in the country. So we get to test a lot of this for the factory. But we're going to primarily talk about the single stage defrost controls in our residential products on the Trane American Standard products. This is a current defrost control, but a lot of the logic also applies to the older defrost controls. And we do something called demand-based defrost. And we'll talk more about that as we get along. So this big relay, this is our high voltage fan relay. We've got a CBS, coil-based sensor, or a CTS is what it's also called, a coil temp sensor. We've got the outdoor temp sensor. Here's all of our 24-volt inputs and outputs. And then on our defrost control, since about 2016, the low pressure switch has been connected to the board. Prior to about 2016, it was just in the circuit of the contactor. We now run that thing separately into the board. So we have a little more diagnostic capability and a lot more understanding of what's going on in the system this way. So, couple of things that we need to understand is defrost has to have some inputs. We've got to power the RMB of the board. Heat pumps will actually run if you give them a Y signal in heat mode or a Y and an O in cooling. However, the unit will never go into defrost without 24 volts between R and B, the red and the blue. Okay, so active heat call is a Y only call. Cooling call is a Y and an O. And then, of course, we need defrost sensors. So we have two sensors for demand defrost, an outdoor sensor and a coil temp sensor. And we'll talk more about how that decision is made in just a minute. But a couple of things that you need to understand is in the service facts, there's always a demand defrost quick specs, and it tells you everything that that board is looking at, whether it's times, temperatures, all of that. And there's some good information. We'll talk a little bit here over the next few slides. One of them is what outdoor temperature must we be below to allow defrost, and what coil temp must we be below to allow defrost? Well, the outdoor temp, we have to be below 52. If we're not below 52, the system will not allow defrost. So if you're out on a job and it's 55 degrees outside and you're tarping the unit to try to get it to freeze up to check defrost, it isn't going to happen. The other thing is the coil has to be below 32 degrees, because if the coil's not below 32 degrees, we do not have ice forming on a coil because water freezes at 32. So we have to have that coil below 32 degrees. So those two conditions must be met before defrost is allowed. All right, so once defrost is allowed, we have a couple of timing things that we're shooting for. And again, this is in these demand defrost quick specs. One of the things, minimum time for defrost. When we go into defrost, we will run a minimum time for defrost, and that's usually around 1 minute. Now, target time for defrost depends just a little bit on some setup configurations, but normally we're shooting for about 3 to 4 minutes in defrost. And the board has an algorithm that watches that timing and it starts to adjust the coil temp and outdoor temp sensor set points for defrost to try to target that 4-minute defrost. Okay. Now, we do have a max amount of time for defrost. So we will not allow a system to stay in defrost more than about 10 to 12 minutes, depending on the version of the board. That's one thing that these specs come in real handy for when you're looking at different systems, and it's always in the service facts. Generally, it's 10 minutes, but we do have a few boards that reach out to 12 minutes, and there's a couple of them actually go up to 15 on our variable speed product. But generally, we're looking at a 10-minute maximum defrost time. We also have low ambient lockout put into these boards, okay? And so a lot of our boards will shut down the compressor at a certain outdoor temp. Usually it's about -7. Some of the boards do go up to -12. And then once we hit 3 degrees outdoor temp, we will allow the compressor to come back on. So with these systems, you don't need to set a compressor lockout on your thermostat. The system will take care of itself. Now, low pressure bypass. It's not uncommon to have a low pressure switch when we're coming in or out of defrost. And on the early models, we bypassed for 1 minute, and we found out that that wasn't really long enough. So in about 2017, I believe, we changed that low pressure bypass in and out of defrost for 3 minutes. So now we just ignore the low pressure switch tripping for about 3 minutes because when we go in and out of defrost, we may see that suction pressure crash. And if it drops low enough, it will open that switch, but it's usually only for about 30 seconds to about 1:15 minutes. And in the Pacific Northwest, specifically central Washington, southeastern Washington, western Idaho, and a little bit of western Montana and northern Idaho, we can see some issues where that low pressure switch was actually tripping for at about the minute to minute 30 mark. And so we had to extend out that low pressure bypass to 3 minutes. So all of the new boards are 3 minutes. And this is what I'm talking about. So originally the 7255 was one of the first boards released, and now we're version 8177. And those boards, we did adjust that bypass to help take care of some of those challenges. So big thing to note if you're having some odd pressure trips. All right. One of the sensors that were required is the outdoor temp sensor, and that's the black sensor with the wires. Now, up until a few years ago, we would hang this sensor right out the bottom of the control box, just like that. This is our liquid line service valve. And we had some inconsistencies. Now, I understand we did this on the Train American Standard products for 30 years, hung this sensor like this, and it worked okay. If we folded it up tight like this, it worked better. But unfortunately, you know, the reality is the factory guys, they're people and they make mistakes and they forget to do things just like all of our people out in the field do. And sometimes they didn't get folded up properly, or something get pushed up against the liquid line valve here, or get too close to the liquid line valve, get some heat off of that, and it would cause some unusual readings. And so we had some inconsistencies. In order to be better at defrost and do a better job for our customers, we actually switched a few years ago to this style of defrost sensor. It's a little heavier, it takes a little more to adjust its temperature, and it isn't as affected by the piping as much. And it gave us a whole bunch of consistency at the factory production level so that every system was coming out with the same exact sensor positioning. So we're able to manage that better. Now, one thing that will really cause some interesting things to happen with outdoor temp sensor readings is if we don't insulate our vapor line properly. And this happens a lot. because in the heating mode, this is our discharge line. So this is our hot gas line. So this thing's running 130, 140, 150 degrees right here. And then we put the little cover plate over these service valves, and it traps the heat in there. And now all of a sudden we start getting more heat off of this line, affecting that sensor. Well, okay, so it's only a 3, 4, 5 degrees that it affects it, but that's enough to cause problems and inconsistencies in our defrost cycle. So try to insulate your line all the way up the service valve, just like that, to help improve defrost and improve the reliability of the system. The other sensor we need is the coil base sensor or the coil temperature sensor. You'll see it labeled both in the systems. Most of the older systems, it's called the CTS or coil temp sensor. Some of the newer systems, it's now called the CBS coil base sensor, and it's because this sensor usually sits on the bottom circuit. Now, in the old systems, we just took this sensor right here and we stuffed it up inside this copper tube that was brazed to the bottom line. And it worked okay most of the time. And we'd throw a little zip tie around the bottom. But what would happen is technicians would go out in the field and they'd cut that zip tie to change the sensor, and then they wouldn't put that zip tie back in place, and eventually that thing might vibrate out of there. The other thing that would happen is, again, these units are built by people. People make mistakes, and they'd pull that wire too tight, and it would cut into the sensor wire on that tubing edge. Even though you can see it's flared just a little bit at that this piece of tubing right there at the bottom next to my red dot, it would still cut through over time. The other thing we'd have happen is, you see how this sensor shaped with the wire that comes down across the back of the sensor. Well, right here is where that thermistor is actually sitting inside this black sleeve. Well, if this got towards the outside of this well instead of to the pipe side of the well, we might have some inaccurate readings. And again, these are built by people. People make mistakes. They get new people. Things happen. So in order to improve consistency, the factory has switched to a snap-on type sensor. And so you might see something like this on your units now. Some of the units, we've actually gotten rid of the well completely going forward. But this is what we're doing now to improve reliability and improve the overall function of the system. And so now it's a clip-on sensor. And it's just clips onto this little 3/8 line for coil temp sensing. All right, so let's jump into, we're going to run through sequence of operation really, really quickly because quite frankly, it's kind of dry and boring, but you guys need to understand it. So, all right, first things first, we got to have 24 volts to R&B. Again, the compressor contactor will close and operate the compressor without 24 volts on R&B. So it's very important that we get that, because without this, it will never go into defrost. And it can be really difficult when one of the FSRs comes out to the job because you've changed the defrost control board 3 times, and we show up and this LED on the board is not lit, and we say, hey, check 24 volts, and we don't have 24 volts on that board. And we say, well, you got to get 24 volts to the board, otherwise it'll never go into defrost. And people say, well, but the unit ran just fine, except it won't defrost. Yep, that's correct. Without 24 volts, it will not defrost, but it will run in heating and cooling. And this usually happens during the summer when they hook it up, get it up and running in cooling mode. And then wintertime comes around and the unit freezes up multiple times. They change sensors, they change boards, can't figure out why. And then we find out there's no 24 volts, broken wire, what have you. So if you're freezing up, that'd be one of the very first things I'd check. Do I have an LED? If I don't have an LED, I'm checking R&B, see if I've got 24 volts there. All right. So having said all of that, If you install the heat pump with only 2 stat wires, you attach B to ground on the unit, run O to O, and you use the Y wire for Y and R to give that board 24 volts. Defrost will only happen if there's a call for compressor. And every time you reset 24 volts, it's going to reset the defrost algorithm. So you're going to have some performance issues. Sometimes it'll defrost, sometimes it'll freeze up. So that's not recommended. It's recommended that you get a direct 24 volts to RMB. Hopefully that clears some things up for people. All right. Like I said, low pressure switch up here at the top. This is our, goes right into the board. It used to be on some units, it was in the common line right here. Other units, it was in series with the high temp switch and HPCO. Since about 2016, it ties directly to the board. Then we have our coil bottom sensor with the yellow, and we have our outdoor temp sensor with the black. Those tied directly into the board. And by the way, before I move on real quick, the coil, the outdoor temp sensor is the black wires, and if you'll notice on the board, it looks like the pins are set far apart. That's actually accurate. If you look at the board, this is a 3-pin board, 3-pin connector, but the center pin is missing. On the CTS, it's a 2-pin connector, so you cannot get them swapped. All right. So we're not going to be focused on the O because O is for cooling. We're going to focus more on the Y circuit and the W circuits going forward. If we have 24 volts on O, the unit will never go into defrost because it's in cooling mode. So just remember, we energize the reversing valve in cooling mode. So we come from our thermostat Y1 to Y1 on the air handler. Now, some air handlers have a Y out, and we will run on the Y out to the Y of the control board. If we don't have a Y out on the air handler, that's fine. We're just going to wire from Y1 on the stat to Y1 on the air handler to Y on the outdoor unit. And then we run up into the board, and we will talk about these relays here in just a few minutes, because those K1, K3, and K2 relays are all for defrost. Once we get a Y signal, we're going to get a two flash on our control board, and that will provide a notification that we're running in heating mode. So that's 2 times per second. So on the K3 relay here, Y comes up into the K3 relay. This is a normally closed set of contacts, so it passes directly into the high temp switch. This is right on our discharge line of our compressor through our high pressure cutout to our compressor contactor right here. Okay, and of course, common ties to the compressor contactor as well. Let me back up just a minute because I skipped the K2 relay. The K2 relay, this is our outdoor fan relay. So this is that big bulky relay that I showed you at the beginning. Now, some of our units do use a variable speed fan motor. So this is actually a very small relay, just a couple of 1/4-inch spade connectors right on the board. But anything with the PSC, it's going to be that big bulky relay. And that's what the K2 relay is here. And we'll talk more about that as we talk about defrost. So as we're running the system, we've got the compressor contact energized. What happens is the defrost control now watches the outdoor temp and the coil temp and determines when we need to go into defrost. And I'll show you a little more about this here in a minute. But remember, we got to be below 52 degrees on our outdoor temp and below 32 degrees on our coil sensor in order to make sure that we're below enabled defrost. Because if we're not below those temps on both temps, we will not defrost. Once we get below that, it starts to watch those temperatures and it'll decide when we need to go into defrost. So once the outdoor coil needs to go into defrost, first off, the control closes the K1 relay, which sends 24 volts to the O, and then it also sends 24 volts to the X2 wire. That's our black wire, which goes and ties to our indoor heat. Okay. Now this is showing some optional outdoor temp sensors. Most people don't do that around here, but you could do that if you wanted electric heat to fire based on outdoor temp. Not a lot of people do that. Those are extra outdoor sensors. I see it very rarely. But you might see those back on systems that were installed in the 70s, 80s, really old systems. But today, most people don't do it. Anyway, and then we off of X2, we're going to tie into W1, 2, 3, whatever we need to fire up the auxiliary heat. And that's how we fire our auxiliary heat, is actually off of the Y circuit through this K1 connection right here on the board. One quick note about the K1, this is what they call a snubber circuit. So unless you're using a true RMS meter, you might get a false 24 volts when the unit is not in defrost on X2. If you ever get that and you think you have 24 volts on X2, hook a load to it, meaning hook a contactor to X2 and common. Does it close? Probably not. That means it's a ghost voltage, and that snubber circuit voltage will just disappear. It'll collapse and go away. So just be aware of that. Now, the other thing that happens during defrost is we are going to open our K2 relay. This is normally closed, so the fan runs whenever there's a call for the contactor, unless K2 opens. So we're going to open K2. Remember the 3 actions of defrost. Put the unit into cooling mode, shut off the outdoor fan, and turn on the auxiliary heat. That's the 3 actions of defrost whenever we go into defrost, and every system should do that. Now, you'll notice that we keep the contactor running. In some units, we will actually shut off the contactor for about 30 seconds while we're shifting the switchover valve, and that helps with some of the compressor noise on certain systems. We did that a lot in the early 2010s, and by the time we came out with this board, we kind of quit doing that because we figured out how to make the compressors quieter during defrost. So that's essentially the sequence of operation for defrost. So when the coil bottom sensor reaches defrost termination temp, we will terminate defrost, which means we're going to open up the K1 relay, close the K2 relay, and allow normal operation to continue. Go back into heating mode. So no more power to the X2, no more power to the switchover valve, fan starts back up. Okay. All right. Now, we will do about a 12-second delay on the outdoor fan motor. So we fire up the outdoor fan motor, then 12 seconds later, we switch the switchover valve and turn off the auxiliary heat. We do it that way because that helps drop the compression ratio, and so we don't get that as loud a compressor. Like I said, we used to shut the compressor off, but that's pretty hard on compressors, starting and stopping them every time we got to go into defrost. And during the dead of winter, we might have 8, 12 defrosts a day. So that's a lot of extra starts and stops. This way, it does a better job for compressor reliability and still keeps the system quieter. All right. So we close K12. 12 seconds later, we open K1, and we're off in normal operation. All right, so let's talk about some defrost troubleshooting. All right, these controls look a little different, but they are interchangeable. Okay, so we still have our K2 relay, the big blocky relay. We still have our 24 volts here and here, low pressure switch here and here. We've got our coil temp sensor here, or excuse me, our coil temp sensor here, and our outdoor temp sensor here. So realistically, they're the same. And on this side, you've got this smaller coil temp sensor here, the larger ambient temp sensor here. Now, understand we did adjust our low ambient lockout on some of the controls. Some of the older controls, oh, they got a typo. Some of the newer controls were at -12. On some of the original ones that we released in 2016, they were at -7. Okay. And again, we bumped that low ambient bypass to 3. Now you'll also notice our low ambient resume changed as well. So we went from 3 degrees to -3 degrees. So we're going to actually allow this unit to fire back up when it's below 0 outside. Talking about the coils or the temp sensors. The source voltage for the temp sensors is 3.3 volts. On some of the older units, it was 5 volts. With these on the older boards, the pre-2016 boards, it was 5 volts. You can always verify the sensor by going to the plus 3.3 solder dot here and to ground right here, or you can remove the sensor and measure across the terminals. You should, if the sensor removed, you should get 3.3 volts between these two terminals. Same with these two terminals. These are our force defrost terminals and test point terminals. So that's 2 ways of verifying your source voltage. If you unplug the sensor, you have 3.3, and you plug the sensor back in and it goes to 0 volts between these two, double check your connection. Needle leads are a fantastic item when you're troubleshooting, but you likely have a shorted sensor. Unplug the sensor, check the ohm value of the sensor. Generally speaking, our sensors are going to be 10 k ohm at 77 degrees, or an easier way to test is dunk them into ice water, swirl them around for a minute. You should be at 32 k ohm. So 32 k ohm at 32 degrees. That's the fastest, easiest way to verify sensors. All right. So there's a perfectly defrosted unit. We're about to go into defrost. Okay. So we're going to, because we're in heating, we're extracting heat from the air. This coil temp during heating mode is below outdoor temp. So we're taking heat from outside the air. Once we drop below 32 degrees and we drop below dew point, we're going to collect water. And at 32 degrees, we're going to start to freeze said water. So ice acts as an insulator. So the more ice we build up on this coil, we get less heat out of the system. The other thing that happens is our temperature on this line begins to drop. So when you think about as this unit freezes up more and more, our coil sensor and our outdoor sense temperatures are going to get further and further apart. And when they get far enough apart, the system's going to go, hey, I've got too much frost. I need to go through a defrost. And so then it goes through a defrost. We melt off all that water, warm up the coil just a little bit to dry it out, and then we go back into heating. So that's just kind of an overall thought process of demand defrost. So coil temp, outdoor temp, when those get too far apart, it says, I need to defrost. So in that, we've got an orange temperature right here at about 12, 13 degrees outside, and it's going along here and running just fine. And you can see the coil temp on this gray line begins to drop as we're running the system in that cold temperature. And our coil temp begins to drop and drop and drop. And at this point, it says, hey, you know, my outdoor temp and coil temp are now about 16 degrees apart. I need to go into a defrost, so it fires defrost, and immediately our coil temp comes up because now we've switched to cooling mode. We're now sending hot gas to that coil. And then once we peak out at our defrost termination temp, we reset, we fire back into heating mode, and we drop back down, and we start the process all over again. Now, one cute little thing here you'll notice is every time we end defrost, our outdoor temp sensor bumps just a little bit. That's because of the heat of defrost. And those lines are getting warm. That liquid line's getting warm. And we're getting a little effect on that. We know that's happening. We account for it. It's not an issue. All right. So, generally speaking, the control is looking for anywhere from about 10 to 20 degrees difference between outdoor temp and the coil bottom sensor. Okay. So that coil temp and that outdoor temp are looking somewhere between 10 and 20. Now, the system is constantly going through a learning routine, and it's watching what it did on the previous defrost and its runtime and how quickly that sensor is dropping down in temp. And it's making decisions for defrost and adjusting that range of 10 to 20 to try to hit that 3 to 4 minute defrost cycle, because that's our optimum defrost cycle for efficiency. In this case, we hit a 16-degree delta before it went into defrost. All right, so defrost termination temp. Actually, we're going to talk about soft switch here. I told you that there's a 12-second delay coming out of defrost in which we shut off the outdoor fan and then we de-energize the reversing valve, and that helps quiet the systems. In really cold temperatures, we could have some issues with the reversing valve not shifting properly all the time and maybe hanging up a little bit. If we're having that, we can cut the the JPR1 jumper right here. And yes, it is a resistor. You just clip it and separate it a little bit. You cut that. It removes that 12-second delay. Now, the challenge behind that, it's now going to make it the defrost coming out of defrost louder. We're going to get a little more liquid flood back into that compressor for just a short amount of time, and we're going to get some compressor noise out of it. So we may not want to do that unless we absolutely have to. As an FSR, before I took the role of running the team, I managed Eastern and Central Washington, Idaho, and Montana, and Alaska, some of the worst defrost areas in the country, some of the coldest temperatures in the country. We rarely dealt with this jumper, almost never. So realistically, I don't see most of you ever needing to cut this jumper. JPR2, on the other hand, is a little different discussion. Some of you may end up having to manage this jumper, okay? If you are in Central Washington, meaning Chelan down through Yakima, and then across southeastern Washington, Yakima through Walla Walla, down into Boise, maybe into Coeur d'Alene if you're right near the lake, Libby, Kalispell area in Montana, even down into Twin Falls right on the Snake River, you may have to cut this J2 jumper. Most of you will not. And there's a couple places in Bend and Western Washington that we may have it as well. Excuse me, Central Oregon, I guess, Bend area, that we may have to cut this jumper. But realistically, those areas, it's pretty rare. It's usually right when we're sitting on the water. We'll talk about that in a minute. But normal defrost termination temp, when it's in place, is 47 degrees. That's when we end our defrost. Now, we do have the maximum time limit, but we always want to end defrost on our temp, not on time. If we're ending on time, that means we've got a problem with the system and we're not defrosting correctly, or we've got a sensor issue. If we cut that jumper, that defrost termination temp goes to 70 degrees. And I've had people say, well, I just cut the jumper even if I don't need to, just to make sure that this unit defrosts all the way. I want these clean as can be. Well, the problem behind that is now our average defrost time goes from 3 to 4 minutes to 4 to 7 minutes. Well, that doesn't sound like much, but remember, when we're in defrost, we're running the system in cooling mode. So we're extracting heat from the house to melt a coil and warm up the coil, and we're running auxiliary heat. So we are in the least efficient operation possible, right? Because we're running cooling and electric heat, and we're trying to heat the house while we're running the heat pump and cooling. So it's the least efficient possible. So we want to be in defrost as little time as possible. So we don't want to cut that jumper unless we really need to. If you're in Central Washington, some of those other areas in Idaho and Montana, yeah, you're probably going to need to do a bunch of cutting of that jumper. For the most part, the Washington territories of Central Washington, Eastern Washington, and Western Idaho, they pretty much have to cut these jumpers all the time. We'll talk about that more here in just a minute. All right, so let's jump a little more into the defrost diagnostics, starting with the fun. Some of you may have seen a unit like this. This is what we call banding. Unit has gone through defrost. Matter of fact, this one probably just barely finished defrost, and it looks like this. It did not complete defrost. We verify the coil temp sensor, we verify the outdoor temp sensor, everything's correct. So is this a board issue? The answer is no, probably not. And this is what I'm talking about with the J2 jumper. Now, what happens in some of those areas that I mentioned is we end up with freezing fog, meaning that we have fog roll in and the outdoor temp is below 32 degrees. Now, we get this in all of our territories. Usually comes in, rolls in for a day or two, and then it rolls back out, no problem. That day or two, we might have some units that band like this. Okay, not a problem. Within a day or two, the fog's gone, the banding goes away. In those areas that I mentioned, the problem is the fog will settle in for 3, 4, 6 weeks at a time. And so we have a unit that looks like this for 6 weeks, and it's fairly inefficient. And so we will have to cut that J2 jumper to increase that termination temp on that coil temp sensor so that we completely clear this coil. Now, with the variable speed products that's shown here, we actually worked with the factory back in 2014, and we now have a low, medium, and high defrost temp. Low is the factory setting at 47, high is 63, or 60, excuse me, high is 60, and medium is at 53 degrees, about halfway in between the two. So some of you in Western Washington, Western Oregon, if you have some of this issue, you may need to bump it to medium. For the guys who cut the J2 jumper all the time in the areas in Washington, Idaho, and Montana that I mentioned, you're probably going to have to go to high every single time. So this is not a sensor calibration issue. This is an environmental issue. And we have people that call in and say, hey, we've replaced the board and the sensor 2, 3, 4, 5 times, and it still won't quit doing this. Like, well, if you changed it once, it's probably not the issue. If you change it twice, it certainly isn't the issue. We'll stop changing parts and find out what's actually going on, right? So staying with our banding, there are some other ways for this to happen. So some things that this could cause this. Low refrigerant charge. If you're not in an area where we have freezing fog, low refrigerant charge is one of the most common culprits. All right. And it's just purely that we can't get the temperature high enough in the entire circuit to defrost properly. Our number two is restricted airflow. Poor indoor airflow performance equals poor condenser performance. And so if we have poor condenser performance when we go into defrost, we may not get enough heat into that outdoor coil to properly defrost. We could have an imbalance in refrigerant flow through our circuits. We'll talk more about that in just a little bit. We may have to relocate a coil temp sensor to a cooler circuit. Not very common. We've seen it a little bit on the side discharge 15 and the 19, but it's pretty rare. We could have that freezing fog happening in certain areas. Again, if it's just for a day or two, I don't recommend cutting the JPR2 jumper. It's not worth it. We could have recirculation of air around the outdoor unit, causing poor evaporator defrost performance. We could have strong winds that's keeping that coil cold. If you're out in a windy area where it's just constantly blowing, Great Falls, Montana is a great example of this. We may not always defrost properly. So a windshield, like a fence on the prevailing wind, is one of the best strategies to solve this. Sticking reversing valve not shifting properly, that could cause it. Outdoor fan not dropping out during defrost because we've got a stuck relay on the defrost control board. That could cause it. So there are some different things that can cause banding like this. And so we need to do our due diligence before we just start replacing boards or replacing sensors or cutting jumpers. We do want to do our due diligence before we start doing that. All right. So as we continue down our frozen coil path here, would you do the diagnostics the same between these two units? And the answer is yes. So while the frost has pushed outside of the unit, we never want to see frost outside of a unit like that, even with, irregardless of a banding issue. But our diagnostic path is the same. We want to verify airflow. We want to verify our circuits are balanced. And we'll talk more about that here in just a minute under refrigerant flow. But we want to go through all of our steps. Indoor airflow is another critical step. Our refrigerant charge. Let's clear out this coil completely. To check refrigerant, we're going to have a clear and clean coil. Then we can fire up the system, let it run for a bit. We're going to gauge up on our discharge and our true suction here, and we're going to reference our charts in the service facts that are going to get us kind of close. Remember, you got to verify airflow before we can verify charge, because if airflow is not right, we'll never get charge correct. All right, so let's jump into refrigerant flow just a little bit. When you look at a coil, we've got a vapor line header here that circuits of the coil tie into, and then we come out of our TXV on our distribution tubes and we tie into the other side of the circuit. So on our bottom circuit here, we come in on the bottom of the circuit here through our expansion valve in heating mode. We run through that circuit and we come out on circuit 5 right here and tie into our vapor header. All right. So if you look at all of the vapor header connections, 1 through 5 here, all the purple ones, those should all be within about 3 to 5 degrees of each other. Okay. If you're running, just for simple numbers sake, you're running 40 degrees here, 40 degrees here, 22 degrees here, 40 degrees here, 40 degrees here. Wait, we got a problem. Why is that one running 22 and the others are? That means we've got restrictions in the circuits. Okay. And same with the blue side on these red circled areas. All of these should be within about 3 to 5 degrees of each other. Our coils are pretty balanced. Okay. You might find a defrost problem and circuit 5 here, the bottom circuit that our coil temp sensor is on, never freezes up. Well, that means we've got a bad circuit in coil circuit number 5. The rest of them are frozen up, but 5 is not. So we won't get proper defrost. We won't properly terminate defrost, and you'll freeze up a coil. So it's very important to verify these as part of your troubleshooting process. Now, this was a fun picture from one of our field trials. What's wrong with this picture? Well, we had water draining right onto the unit. And as you can see, it froze up and basically blocked the airflow of the unit. So what happened? It froze. And when we start looking at components of failure, well, what component failed? Well, it was the install that failed, right? We might end up killing a fan motor. That might be the complaint. We might end up with a complaint that the unit's not defrosting properly or frozen up, and you come out, swap out the board and the sensors, and now all of a sudden you come back a few weeks later when we've got rain and freezing situations, and we've got a frozen unit again. And you can chase your tail. So make sure we're watching the overall install. Okay. All right. This was actually a job that I went on years ago. And we were having a lot of noise issues with the noise complaints from the homeowner, high utility bill complaints. And this was a variable speed outdoor unit. And you can see we're not defrosting well. What we found, you can't see it very well in this picture. They needed to use the other picture I sent them, but you can see right here, there's a little bit of shadowing. What that was is an ice dam. This unit sat right in the corner where 2 pitches of a roof met, and the water drained right down the side of the house, drained onto the unit off of 2 different roof eaves. And so the reality of it is we couldn't defrost properly with this system. And I believe the homeowner said that it sounded like they were making margaritas outside every so often with the ice rumbling. Well, that's because the water would freeze onto here, it'd start up, and ice would fall onto the fan blade. All we did is we moved this unit about 10 feet to the north, and all of our problems went away. So make sure you're watching for those type of issues. This was another one. We had a fence that was right in front of this unit, and we ended up with recirculation. We had snow blocking it off. This was in a deep snow area. They put 3-inch pump ups under this thing, and you can kind of see the snow drift just a little bit right here. But there was about a 3-foot tall snow drift in front of this thing, plus a deck that was right out here in front as well. So we ended up basically causing recirculation issues. I also went on a job up in Central Washington, and they were complaining that their utility bills were high. And I get out there, and they had dug the outdoor unit out about a foot all the way around it. The outdoor unit to the top of the unit was about 3.5 feet off of ground level. The snow was 4 foot deep. So it was basically in a little bitty chamber, and we couldn't get proper air circulation. So we do need to watch our snow drifts. And they ended up building a awning over the top of this thing about 6 feet above it. Please do not put an awning on an updraft model a foot above the unit, because then you will cause recirculation issues. So this was another one, freezing rain. They want to know how to deal with it. Unfortunately, you know, we have some environmental conditions that will cause us problems. Honestly, about the only thing we could do would be to build a dormer, again, at least 5 foot above the top of the unit to help with that. But there are some conditions that we just can't manage within a defrost control. Of course, this is a temporary solution. It'll clear itself in a couple of days. So as we jump a little deeper into defrost troubleshooting, understand there's fault codes. A 1 flash means a ambient temp sensor is open or shorted. A 2 flash on our red LED means the coil temp sensor's open or shorted. A 3 flash, our low pressure switch is open. It will go away as soon as the low pressure switch closes. So if you see a 3 flash, it is while the switch is actively open. Okay. All right. 6 flash, we have defrost cycles too close together. So this unit is watching its defrost timings. And if our defrosts start occurring within 15 minutes or less of each other, we consider that excessive defrost cycles, and it goes into a timed defrost, and there's a lot behind that. But we've got something going on. I've seen restricted circuits where the coil temp sensor was freezing up too quickly. I've seen bad TXVs cause this. I've seen low refrigerant cause this. So there's some things that can cause 6 flash fault codes. But either way, with the 6 flash, it goes into a timed defrost. And so what it does, if it saw a less than 4-minute defrost, it adds it'll add 5 minutes to the next heating call. So instead of allowing the defrost to happen in 15 minutes, it'll say, I'm not going to allow defrost for 20 minutes. And then it'll add another 5, and it'll continue to do this until the defrost cycle is at 4 minutes. Once the defrost cycle is at 4 minutes, if it gets below that, it'll start to subtract runtime. Either way, this is not a good situation. It'll also enter this if we have 9 low pressure cutout trips in one call for heat. We'll talk about that here in just a second. 9 flash. 9 flash just means it got too cold outside, and the unit has shut itself down until it warms up outside, and it's going to fire the auxiliary heat whenever the 9 flash happens. Okay, so if you see a 9 flash fault code and it's 40 degrees outside, what should you be checking? Well, first thing I'm going to check, my outdoor temp sensor. Because if my outdoor temp sensor is reading negative 30 degrees, yeah, the 9 flash should be happening. If it's not, I'm going to dunk that sensor into ice water, twirl it around, make sure it reads 32 k ohm in that ice water. Because if we've got a broken seal on a sensor, it may read fine when the sensor's dry, and it will read incorrect when it's wet. So I'm going to dunk that thing in ice water, make sure it reads 32 k ohm at 32 degrees. If it does, I'm going to replace the control board. If it doesn't, I'm replacing the outdoor temp sensor. What else could cause a 9 flash to trip prematurely? Well, snow. If we get snow packed into that area, I've seen that cause it. So we do need to pay attention to our installs. But usually this is going to be our coil temp sensor or control board. Low pressure switch in cooling. Well, low pressure switch trips in cooling is usually airflow or refrigerant related. Could be low ambient though. If we're running the system in a low ambient cooling situation, we could have some low pressure switch. So we have soft lockouts. The first trip, it does a 15-minute soft lockout. You get a 5 and 6 flash. Second, it goes to 30. The third and the fourth trips in cooling, it goes through an 18-hour soft lockout. On the fourth trip, it goes into a 4 flash fault code saying, hey, we really got something wrong. So the reason why we do these soft lockout periods like this is so that if we're having a particular environmental situation, we can get past it. Like an 18-hour soft lockout because the homeowner hasn't changed their filter. All of a sudden, their house is warming up, the system's not running. Most homeowners will go down and check their filter, realize that they need to get a new filter, and hopefully they're calling you for a new filter, or worst case scenario, they're going down to Home Depot or Ace Hardware and buying one. So that's the benefits of a soft lockout cooling. In heating, we have a lot more lockout trips. On the 9th trip, we do go into a hard lockout. Okay. So usually the low pressure trips, remember, in and out of defrost, we ignore it for 3 minutes. So that's not part of this. So this is trips while we're operating. A lot of times this is a low refrigerant charge, or we're freezing up too quickly, something like that. Okay. So one of the benefits to soft lockouts is if we've got a weather pattern happening that is causing us to trip, like a heavy freezing fog with high winds, something like that, we can go through our soft lockouts. In an 18-hour soft lockout a few times in a row, we might get past whatever weather pattern is happening. Not too often are we seeing hard lockouts. On the early controls, if you've got a unit with a model 2016 through about 2019, if you are having hard lockouts on low pressure, please get with us. We need to talk to you about it. We need to check the control part number and see what those are, because we might have a situation where we need to update that control. So get with the FSR team. We'll talk to you through that if need be. Most of our heat pumps, pressure switch opens at 35 PSI, closes at 55 PSI. Most common low pressure trips is going to be the low refrigerant charge. So we get that. We're going to clear the coil, make sure it's a clean coil. Then we're going to verify our airflow. Then we verify our charge off of the performance curves in the service facts. If you ever need the service facts, text in to us. We will get them, get you a link for them, texted right back out. So, like I mentioned, we have the early controls had a 7 and 8, and this was what they called the implied low pressure switch. I will tell you that if you have one of these controls and you're seeing that implied low pressure, it could populate as a low pressure switch trip or a 7 flash fault code. If you have that, get with us. We need to work on that, come up with a solution for you, which is usually updating the control board. But there are some times that this happens normally as well. So if we're below negative 7 degrees on these early ones, we would allow some of the units to continue to run. So, and we're just looking at the defrost timing. So a couple of things to verify on 7 and 8 flash before you give us a call. Verify the sensor positioning and calibration. If you've got one of the coil temp sensors that go in the well, make sure that thing's turned towards the pipe, not away from the pipe. Insulation on the vapor line. This was a huge one. Verify charge. Usually this is solved by one of these 3, okay? And then also make sure, verify your refrigerant charge, superheat, on your outdoor expansion valve. And then of course, verify your defrost operation. Make sure we're not freezing up oddly. So that's everything I have for you today. If you have any questions, feel free to raise your hand or type something into the chat. Other than that, have a great day and thank you for coming.